Hey everyone, welcome to the Howdy Partner Show. I'm Kriti here today, a Partner Solutions Architect from Amazon Web Services. With me, I have my co-host Art. Art,
Hi everyone. Hi Kruti. So excited to be on the show today. I'm back. For all the new watchers, new viewers, my name is Art Twazan. I'm a Partner Solutions Architect alongside Kruti, reporting from sunny Seattle. I see that in the comments. So for once, I think the weather is coming in strong and it's springtime. So I hope, and I think I see like sun on Kruti's side too. So it's a good Wednesday.
yeah, that's true. It's sunny here as well in San Francisco. And today we also have a guest from AWS, Parminder. Let's also welcome him on the stream.
Thank you, Art and Kruti. Nice to meet you all. And thanks for arranging this, Kruti. Yeah, myself, Parminder, I'm based out of Dallas, Texas, and I'm glad to meet you all who are listening to me. And today's show is all about chemistry, and that with a company called as Good Chemistry, right? So chemistry is good nowadays. And back in my high school, chemistry was the most difficult topic for me, at least. But speaking after 25 years on a chemistry, this is the one of the company who I love most among the other ISV partner who I deal with. But before we go with the good chemistry, what I want to detail out here is like, how do I work with my partner? A partner is an important ecosystem for AWS growth when we think about like how to expand our business. And specifically on the quantum side, our team, the WWSO team, and the bracket team, which we have quite new team, and I joined this team last year. I've been AWS for last 4 years. I'm still studying my master out of university in Spain, and this was a natural progression for me to support the quantum partners since I was supporting one of the global system integrator in my previous role. I live in Dallas, Texas, and with that, Kruti, why don't we invite good chemistry folks and start the discussions?
Yeah, awesome. Thank you so much, Parminder, for that introduction. And as many of you might have noticed, we don't have James here on video today, but he's definitely on the chat. So yeah, if you want, you
Yeah,
can
he's
talk.
with us.
And we also have James from Good Chemistry, who'll also be on the chat. So if you want, you can talk to James from both the companies. And with that, let's quickly bring in Valentin and Nicole from Good Chemistry. And Valentin, you're live, and Nicole, you as well.
Howdy. Hello, everyone. Howdy, howdy.
Thank you so much, both Valentin and Nicole, for joining us here today. Really appreciate your time here. And yeah, so could you tell us why are you here today and what is it that you're going to show us? Give us a little introduction of yourselves and about Good Chemistry in general.
Okay. Maybe we can start with ourselves. I think that's easier. Hello, everyone. My name is Valentin. I've been with Good Chemistry for about 5 years. Back then, we used to work with a company called One Qubit, and we spun off essentially as the chemistry division. And I'm the quantum software lead. My background is in applied mathematics, HPC, and well, now I do quantum computing and chemistry.
Wow. Yeah, I have no idea about quantum computing
No,
or
not
chemistry.
at all.
We'll try to get a vague idea, but fortunately, most of what we're going to talk today is not about quantum computing. Nicole,
Okay.
you want to introduce yourself?
Yeah, absolutely. Hi, I'm Nicole. I'm a software developer here at Good Chemistry. I've been with Good Chemistry 2.5, almost 3 years now. And my background, I have a degree in computer science and one in chemistry. A bit of a weird combo, but it works really well for what we're doing here. And before Good Chemistry, I also spent a year working in the pharmaceutical industry. I was doing computer-based drug discovery for a pharmaceutical research company called Admar Bioinnovations, based here in Vancouver. Now at Good Chemistry, because we're a smaller team, then I get the fun of touching almost all parts of our stack. So I've done everything from write app code to do AWS infrastructure to networking. So it's really fun to be here after working with the AWS ecosystem so extensively.
Awesome. Thank you so much, Nicole and Valentin. Yeah. So what are we going to be seeing today? What is the solution that you bring to the table?
First, maybe we can get a few words on what we do at Good Chemistry overall. So Good Chemistry is a software company that is trying to push the limits of what is possible with computational chemistry, essentially to solve tough problems. A number of them have to do with essentially make a world a better place with designing better materials, designing new drugs that can really help people, and also tackling tough stuff that can be related, for example, to climate change or people needs, such as water capture, carbon capture, maybe the design of better batteries, the design of better materials. So it's applicable to a wide range of problems in industries that Nicole will talk about a bit later.
Awesome. Cool. Well, before we get into kind of the products, I'd love to learn just a little bit about Good Chemistry. You know, your titles and your backgrounds is so special and unique. And obviously I would never have thought like chemistry and computer science kind of go together. So when you're talking about like the problems that you're facing, like why do we need to use like quantum computing, or I think HPC, you mentioned high performance computing for these use cases, like how long does it usually take? For either Nicole or Valentin on that.
Yeah, I can take this one. That's a really good question, especially given that I'm assuming most of our viewers probably aren't chemists or in the material science field. So as Valentin mentioned, material science is widely applicable to our lives. It's basically the development of any new material, what we eat, what we wear, drugs, green energy, fuels for our cars, heats our home. But we're focusing on shortening the innovation cycle for developing these new materials. I actually have a slide and an example I can take you through to really nicely illustrate this problem. Valentin, do you mind?
Yeah, let's pop it up.
Yeah.
Sure.
Give us a minute. And I'll go for it. So let's say that you're a material scientist. Let's say that you're a researcher at a pharmaceutical company. I'll chat as you get the slide up. So let's say you're a researcher at a pharmaceutical company and you're trying to create a new drug. So how would you do this? First, you would identify the properties that you want your drug to have. You'd want it to bind to a target protein in the body. You definitely want it to be non-toxic, and you'd want it to be stable so your drug could be stored and transported. So given this set of properties, you would then design a set of candidate molecules that you suspect would have these properties. That's probably based off other molecules in nature that have similar properties, scientific studies, or materials you suspect would have the properties based on your chemical knowledge or chemical intuition. Once you have your set of candidates, step 3, you would take these and synthesize them in the lab, and you would test them to see if they actually have the properties you're looking for. After testing, and this is actually a big if any of the materials do have the properties, you can take those molecules, iterate on the design to create a new set of candidate molecules, and repeat the cycle until you maybe come up with something that's good enough to move forward into the next stage of development. So that's kind of our basic innovation cycle for creating new materials, in this case, a drug. And actually, just to give you guys an idea of the scale here, when I say we're looking at candidate molecules, we could be looking at testing assays up to thousands of molecules. So imagine you're a material scientist, you're in the lab, synthesizing and testing thousands of molecules. That is expensive and takes time. And that's why, as you can see on the slide, the time to take a new material to market can be decades, and it can cost on the order of billions.
Oh, gosh.
Yeah, are you guys following so far?
Yeah, so definitely like a long time. So a person could be working in the same place and it's like specific molecule for literally it could be their entire like career, and it could or could not even make it to kind of the production, would you say?
I mean, you say that, but that's not an exaggeration. In my year in pharma, I did see researchers, and that was their story. Mm-hmm. So given this cycle, Good Chemistry's mission is to shorten this innovation cycle. So I'll talk a little bit about computational chemistry. Looking at this cycle, what if you, as the researcher, could leverage computing to make this workflow more effective? This is computational chemistry. we're basically using computer simulations to investigate and predict the behavior of and properties of molecules. So Valentin, if you could go to the next slide. Oh, you already did. Read my mind. So harnessing the power of computing as a researcher can expedite this process in several ways. Firstly, when looking at candidate materials, you can search a much larger chemical space for possible compounds. I'm talking libraries on the order of millions of compounds to search for molecules that could be candidates. Once you've pulled candidates from this much larger chemical space, you can then use property prediction. And with a computer, you can identify only the most promising candidates to take to the lab for validation. So you essentially have access to more possible molecules, and then you can create a short list of only the molecules that are most likely to be the top performers, the most effective. Once you have that short list, you can take that into the lab, synthesize them, test them, and repeat the cycle. So the implications of this are huge. We're shortening the innovation cycle for new materials to do better chemistry faster and more cheaply.
Yeah, computational chemistry really can help us here. And however, it doesn't come without challenges, because otherwise, I guess, we would have solved that like decades ago. The challenge we encounter in that field is that the algorithms that can give us, the accuracy we need to predict this property, unfortunately scale up pretty badly. Very quickly, as we grow the size of a problem, the size of a molecule, the amount of memory computers need, the amount of operations that need to be carried is blowing up very quickly. Even on small examples, you have to rely, for example, on algorithms that make approximations, or HPC clusters, maybe some accelerators, and it only take you so far. So to go further, people have developed algorithms that make more and more approximation and sacrifices accuracy for less computation, or algorithms that rely on guesses or experimental data that come from, example, chemists. But clearly that's not really applicable or efficient if you need to scan a lot of different molecules, right? So overall, right now, today, we still don't have that combination of speed and accuracy we need to explore this very large space of molecule and make the prediction to recommend a few good ones to take to the lab.
Oh, we have a question on the chat as to what is HPC. A couple of people on the chat helped answer that, saying it's high performance computing, but yeah, would definitely like to hear it from Good Chemistry side.
Sorry, take that for granted. So high performance computing, to short it down, the art of crunching numbers real fast on compute architectures. That's it.
Big numbers.
You can use, just your laptop that has a CPU with several cores. You can use a graphics card to crunch numbers for many things. You can use quantum computers. We'll talk about that. But, the art of using algorithms and approaches that, for example, use many instances as well in the cloud to crunch numbers fast. That's it.
Okay. Do you have any, or will you be showing us any use cases of where this would be applicable in real time? Or
I can detail at least one. Meanwhile, Valentin and Nicole can think of a better one. So there is this whole electric vehicle which are getting a lot of steam in the automotive sector, right? And then there are various techniques to produce battery for this electric vehicle. So generally speaking, getting a make and model of a car in a factory from OEM takes multi-year sometimes, right? Experimentation. Not as large as what Nicole showed, like 5 to 10 years, but yes, there is a cycle which every make and model take few years for experimentation, pilot, and build, right? And with the electric vehicle, it's even more complicated because you need to think of new materials which can power those electric vehicles because there is only finite number of lithium mines out there. Then you have to think of new way to invent fuels or some chemistry composition. So in my humble opinion, in coming years, there is a lot of traction in this field when you want to search for a new material composition for those kind of a setting. So it has a direct impact or the business transformation or an opportunity for those companies who are thinking to make electric vehicle batteries, right? And clean energy tied to that together. That can be one area where this is very valid when you are doing a material discovery and you need a technology which can give you the yield not in years but in weeks or hours, so that you can experiment faster, you can fail fast, and you can move on to the next set. That is what I think research community or research scientists in the lab want. They don't want to wait for the experiment to get over in next few years to see the result, right? They want quick experimentation. So that is where this whole quantum chemistry play important role. Over to you, Nicole and Valentin, if you want to add.
No, I think, go ahead, Valentin.
Yeah, sure. I see a question about naming algorithm used to determine new molecules of material. I think this is a very open question in general. Any new geometries, arrangement of atoms is a new molecule. It's more like computing that property to decide if it's something that meets the expectation or not. I don't have an algorithm to give you. We'll name, however, a few well-known algorithms that are used to compute properties of these molecules. As far as I know, people try a lot of different computations on different types of geometries. They also use machine learnings as well to try to generate new geometries. But that's the extent of my knowledge. I'm not a chemist myself, unfortunately. To follow on what we're talking about earlier, I was saying that, yeah, the reason that we can't just apply computational chemistry to solve all these problems is that when we get to the bigger molecules that are more interesting and to look at all this big space out there, we simply don't have the speed and the accuracy to do that. People have been developing code packages for computational chemistry since, I think, at least the 70s. But they rely on technologies that are a bit outdated, for example, and they haven't really embraced, for instance, the seemingly infinite, not quite infinite, computational power of the cloud and its elasticity, or more recent approaches that have been revived by advances in hardware like the GPU, for example, machine learning. And that is the idea behind the effort we've been pushing at chemistry with this platform, QEMIST Cloud, that Nicole is gonna talk about.
Yeah, I think that's very well said, Valentin. We're certainly not inventing the field of computational chemistry, but what we're doing is taking computational chemistry and bringing that to modern technologies, bringing that to the cloud. The easiest way you can describe QEMIST Cloud is a virtual supercomputer on the cloud for chemistry calculations. And how we've gone about building this thing is we've started with our quantum chemistry algorithms. So at the application level, we've implemented highly accurate quantum chemistry algorithms, but we've designed them to run natively on the cloud. This is in contrast to older algorithms available. So they take full advantage of the parallelism and the elasticity available to us on the cloud. With these algorithms, we then built an orchestration framework on top of AWS's elastic cloud infrastructure so that we can scale these algorithms massively with on-demand and spot cores. So we have highly parallelized algorithms, scalable on demand to massive scales. And we're making these scalable parallelized solvers available as a service to anyone. We're basically democratizing the access to this compute power because you no longer need on-premise HPC hardware. So you wouldn't need, where you would just traditionally need like a dedicated compute cluster. or you'd share a compute cluster if you were, say, a researcher at a university, you can now spin up instances on demand on this platform to run your calculations much more quickly. And with this platform, we're also looking forward by incorporating the latest technologies. We're taking the high accuracy data that we've generated from our quantum chemistry methods, and then we're using this data to feed into and train machine learning models. These models can perform tasks like geometry optimization hundreds or even thousands of times faster. So we're building a virtuous cycle where we're improving our machine learning methods with our classical approaches. We're also looking forward into the quantum computing space. It's the ability to run a quantum chemistry problem on an actual quantum computer. Valentin is here to take you more in depth about that.
I'll try.
Could you give us a brief overview of what quantum computers are before we get into the
I
details?
think it may be easier first to go through maybe a little demo from Nicole about QEMIST Cloud, and then I will have an entire thing about what we're doing in quantum computing and the open source SDK for quantum chemistry on quantum computers, Tangelo, that I'm leading. I think that's going to be a bit clearer for the audience that way.
Okay, sure.
Yeah, I can. What I'll try and do here is give you just an overview of the capabilities of our platform right now, our virtual supercomputer. It's the ability to run chemistry calculations at scale very quickly with on-demand pricing. I'll show you a small example today, but just to give our viewers an idea of the scale and power this platform is capable of, then Good Chemistry recently teamed up with AWS, Accenture, and Intel for a study of environmental pollutants. That's a class of molecules called PFAS. And in this study, we solved complex molecules to chemical accuracy, which is a very difficult problem, previously intractable. And we were able to solve it by orchestrating over 1 million compute cores, 1 million vCPUs to simultaneously number crunch. So virtual HPC on the cloud. And if you guys want to read more about that, I recommend it. It's a very good read. Then we have an AWS blog post. Maybe we can throw the link to that down in the chat somewhere.
Awesome. Yeah, just sent.
Awesome.
Yeah, in terms of like hours, like the whole study, I think, Nicole, it is completed in 9 to 10 hours. And if that study would have been done sequentially, it would probably taken several years.
Yeah, it would.
So that is what we are talking here, like shorten the cycle of the experimentation and fail fast, or have success in shorter time. So that is the key for any business transformation in the field of discovery of the drug or new material, finding catalysts, and so on and so.
Yeah, taking weeks, months, or years off experiments. Do we have any more questions about what our platform is? If not, I can move on to a demo for you guys.
There is a question on, can quantum or HPC be used for crypto since it runs stuff in parallel?
Absolutely. Most of the stuff that has to do with crypto, or you have to actually be more accurate if it's cryptography or crypto in the sense of the blockchain and crypto here. But if it's cryptography, crypto mining, well, technically, it's about crunching numbers in fast and parallel. So yes, can quantum computers be used for that? Well, that's up to people to find algorithms that can run a quantum computer to do something useful. So that would be an area on research.
Yeah. I think today's topic is around chemistry. So I think I will just add one liner here. Yes, there is a scope for quantum in the crypto mining, but more from the because traditionally blockchain is being used for the crypto mining. But I think there is an article, and we can send, and then you guys can reach out to me, whoever has a question. I think, like, to make this sense, the blockchain secure itself through the QKD, you can use the quantum in that sense. Okay. Traditionally, blockchain can be broken. There was an article a few days back, I'm forgetting, it's on archive. But what quantum promise in the blockchain is, like, you will make the blockchain itself unbreakable using the quantum QKD. QKD in this case is quantum key distribution, which is new form of generating the certification of the key without use of the public key. Now, there are elaborate algorithm and literature, but happy to help if someone has a need. Our AWS cryptography team is heavily involved in that side, and even our bracket team. Over to you, Valentin.
Okay, I was done with my blabber. Nicole, if you want to take us back to chemistry.
All right.
Yes, back to chemistry.
So talking about HPC and the interesting applications for it in our modern world, let's bring it back to chemistry and what QEMIST Cloud can do. So if we can switch to my screen, I can actually give you guys a little demo of our platform and a simple worked example here. All right, are we streaming? Yeah, we are, perfect. All right, so what you're seeing here is just our QEMIST Cloud dashboard. It's our web portal. And after the show, we're actually going to give you guys a link where you can follow, sign up for an account on our platform, and get, I think, $10 worth of free QEMIST Cloud credits. You can use that to play around, submit some examples. You can also use this for Tangelo. So we'll drop that link for you guys after. If you follow it, you'll come to a page like this. You'll log in. And once you log in, you're going to hit a page like this. There's a lot going on here, so don't worry, I'll talk you through it. Essentially, what our web portal is a dashboard to look at all of the problems that you've submitted to our platform. So as you can see here, I've been playing around. I've been submitting some calculations for different molecules, and I'm looking at basically a log of different problems I've submitted. You can see stats like their complete time, what solvers you use. You can download your input. You can download your results from here. It's just a visualization of what you've submitted to our platform. Anyway, and if you guys see anything interesting, I can't see the chat right now, so you can just call something out to me, okay?
Yeah, Miss, this is like a little bit of great user experience in my humble opinion, right? We have seen a lot of chemistry experiment out there in GitHub and people doing some of the work, great work, but they always live on the Jupyter notebook or Jupyter lab, right? But the next progression of your algorithm is to make sure that is wrapped under a managed service, under a website. So this is that front end, which Good Chemistry developed from last few months, from last year.
Mm-hmm.
So this is where research scientists can come in and then initiate the workflow rather than through the Jupyter notebook. So you're getting a whole thing wrapped as a white glove managed service, a good front end rather than I like Jupyter notebook, but they are there for a reason. But the next evolution of that is this front end website, great user experience, workflow management.
Yeah, thank you, Parminder. Working in pharma, I've seen some very rough user interfaces for different platforms, and that's not to say researchers don't use them, but we're looking to create a much more user-friendly experience with this dashboard like this.
We have a question on the chat. Can we see the user story of first entry? I'm not entirely sure what that question means. Or does it mean where we get the data from, or where's the first point of entry to put in the data and then?
I interpreted first entry as if you first logged into this platform, then what would you see and how would you get yourself started?
Okay.
Yeah.
Okay, yeah, that's right. New user experience.
New user experience. Okay, absolutely. I think that flows really well with our demo, actually. So let's say I'll navigate to our projects tab here. What projects is conceptually just a way to organize your problems. So you can think of it like folders in a computer. So if it was a new user experience or a new user story, I'll create a new project for us. Let's call it Howdy. Howdy, and the description, this is a demo. All right. So when I create this new project, then as a new user, I would log in, I would come to my log, and I would see it's empty. Okay. So next, as a new user, I can see the front end where I can submit my problems, but how do we actually interact with this platform? So what we've created is, if you go to our download tab right here, then we've created a Python client library. How you interact with QEMIST Cloud is with the QEMIST client library. And what this is it's just a series of lightweight abstractions to help you define your problem and submit it to our service. You don't actually do any heavy lifting with this client library. You could run it off in EC2, like T3 micro or something. It just provides you a series of abstractions. And actually, so what you would do as a new user, you would take this client library, download it, and then you would probably navigate over here to our try tab or to our documentation. We have some great demo scripts that you could kind of use as a scaffold to get yourself going. Mm-hmm. So as you can see, we've got a nice demo script off to the side. In this case, similar to this demo script, I have a Jupyter notebook to kind of demo our client library. So I can switch over to that. Is there anything else that you guys would like to chat about here? All right, let me swap over. All right, so I've got a Jupyter notebook where we're going to use the QEMIST client library to submit a problem to QEMIST Cloud and calculate the energy of butane. For my non-chemists in the audience, why this is an interesting problem or why this is relevant, we talked about materials science and computational chemistry being the prediction of molecules, their properties using chemical simulation. A very fundamental property of a molecule is its energy. Using the ground state energy, you could calculate other properties like reactivity or binding affinity or geometry optimization. So this calculation is a starting point for many other types of property prediction. In this case, we're doing a simple work example. So we're going to calculate the ground state energy of a butane molecule. So the first thing we're going to do is set up our QEMIST Cloud variables. There are two important variables that you need to set either in your Python script or in your environment. One is your authentication token. This is your identifier for QEMIST Cloud. So it ties the problems you submit to your account, and it also controls billing. So the credits that you have in your account or that you share in your organization are tied to this. How you get your authorization token is we would go back to our QEMIST Cloud tab here. You'd go up to your profile up here, and you can click API token and copy paste it from there. So that's your first environment variable. The second thing that we care about, like we heard in our notebook, is the project ID. Remember, I took you guys over to our projects tab and said that projects are essentially folders or a way to organize the problems you've submitted. So to tell QEMIST Cloud which project we want to file this submission under, I'll go to our projects tab and we'll go to Howdy. And here we've got our project ID. So we'll take that, bring it over to our Jupyter notebook and pop this in here. All right, so now that we've told QEMIST Cloud who we are and what project that we want to be submitting problems to, now we can start to use the QEMIST client to define our problem. So as you can see here, I'm importing some different components from...
Nicole, we are seeing your web page rather than Jupyter notebook.
Thank you so much, Perminder. I'm having to switch.
I'm paying attention. I'm learning the community.
Thank you so much for that. All right, so just to rewind a bit, we've put our QEMIST project ID for our Howdy project back in there, and we've set those as environment variables. So now we're taking out this cell and the components that we're importing from our QEMIST client library. So we've got a molecule class, and then we've got classes that define the kinds of solvers that we're using to solve for the electronic structure here. So how we define a molecule in QEMIST Cloud, and this is very common in the field of computational chemistry, is we define a molecule as the XYZ coordinates of the atoms in 3D space. So we're using an XYZ file, reading that into our molecule object right here. We're also setting the basis. That's like the set of functions that we use to bootstrap the calculations later on. Doesn't really matter. We're using a smaller set of functions here. In general, as this set gets bigger, then it gets more computationally expensive but more accurate. It doesn't really matter. We're setting the basis, setting the geometry, and we have our molecule object. So we've got our butane. Now we want to solve the electronic structure. Here we're creating a solver pipeline that we're going to use to submit our molecule. So what we're going to use here is a full CI approximation. Full CI is basically considered the gold standard, the most accurate.
What is a full CI pipeline?
So what we're doing here.
Okay, can you go?
Okay, so what we're doing here is we've defined our problem, the molecule, and we're defining the algorithms that we're going to use to solve the electronic structure solver. So in this case, we're using the IFCI algorithm, which is a highly accurate method. And if you remember earlier, Valentin touched on the idea of cost versus accuracy. To have a calculation this accurate would generally be very computationally expensive. But what we're doing here is we're taking the highly accurate method that we've defined here, and then we're applying a decomposition to it, which is basically taking this one very complex problem and breaking it into a series of smaller, more manageable chunks. And by breaking it into these chunks, that's how we can submit it. That's how we can solve it more quickly using our orchestration framework on AWS. We can submit these chunks in parallel to a series of instances and then aggregate the results at the end.
Okay. And I had another question. So internally, where do we first store our data?
Internally, where do you first store your data?
As in, is it stored on an S3 bucket, or where do we store our data to utilize it for the algorithm?
Okay, so as a user, how we store data, and also as a user, how you would access your data is through our API, which makes a database call.
Okay.
Internally, we shuffle data around in a few places, but the aggregate results at the end you can pull from our database.
Yeah.
So for this case, Nicole, so you mentioned like running it in parallel and separate into chunks runs it like a lot faster. Can you give so what kind of like numbers are we looking at? So if you're running this kind of traditionally versus on the QEMIST platform, like how much time can we anticipate to, like how much faster can we see this?
Well, for James, maybe you can give us an idea of orders of magnitude for problem fragments. We can be on the orders of thousands or even tens of thousands, I believe.
Gotcha. Cool. Okay. When James responds from the good chemistry side, we'll let the team know. And I think we also got an interesting question. So in terms of the coordinates for the molecule, I think, what are the coordinates for? Is it the molecule located somewhere? Like how are you getting like the XYZ for the molecule in question?
Yeah, that's a good question. Basically, you can imagine just our Cartesian plane in 3D space with the 0 axis. And what we're doing is we're plotting each atom of the molecule on this Cartesian plane. It doesn't necessarily matter the position of the atoms relative to each other is what matters in this case, because we're not plotting it relative to anything else. So what you can see here in the coordinates file is the carbon atom and its coordinates on the XYZ planes of our Cartesian field. Does that answer your question?
If you remember your school years when we represent the molecule with balls and sticks, these are the positions of the balls and you know how far away they are to each other, and the program understands how they are connected.
Mm-hmm.
Gotcha. And I can imagine working with like the larger molecules, that the number of like rows for these large molecules is just like a huge list, I'm guessing, of like XYZ coordinates once you get to that like size.
Oh yeah, these can get quite large. That's why we've loaded it in from an external file here. And just to go back to that question asking about orders of magnitude, it really is dependent on the size of the molecule, also the level of accuracy that you're looking for. But using this method, we've taken molecules that would previously be intractable, impossible to solve, would melt your laptop, would take years even on a cluster, and we've made them possible and solvable on the order of hours.
Awesome, thank you. And I think we got some more really great questions coming. I see from the Greek Geek. Kruti, if you could pop that up. So they're asking, can you compare this performance to running a highly parallelized algorithm on traditional multi-core CPUs or GPU compute-based solutions?
I think there was an interesting statement from Nicole. So as someone from, again, HPC, where performance is important to me, comparison has to do with both, I guess, time to solution. Like, like someone in the audience right now is talking to maybe, shrinking that to hours instead of years or days or whatever. And the other side is how much money it costs you, right? Yeah. What was interesting is that maybe we're able to do some problem faster than other solutions, maybe not, it may be problem dependent, but with the compute power in the cloud, most solutions that are not running in the cloud right now couldn't be tackling that. Essentially, we're able to tackle like some really, really big problem that haven't been done before because we had access to million cores. And yes, no namesake HPC, you can think about it as distributed computing and supercomputers.
Yeah. And behind this solution, I think there is an architecture diagram, and that will come out in the blog a little bit more. The variational component of this is when you need the compute, you should be able to starburst that compute in a very flexible manner. That is available generally at the cloud, which is in this case AWS, and then behind the scene you have the EKS with the Kubernetes cluster, where when request is coming in, they are getting spawned multiple pod. It finishes a job, it's done. You're controlling the cost like that. So it's like a seasonal variation. When the experiment needs it, you cloud burst, you scale back, and your experiment needed it again, you do that multiple times, right? And then this is a little bit not easily doable in the on-prem world because you have to get all the compute provision upfront and then create your data center and all that. So that is where this high performance computing on the cloud is very attractive when you need to want to scale on the CPU side, or if there is like a training and inference for the machine learning with the GPUs. So that is what I think we are very loosely saying it here, virtual supercomputer, virtual in the sense on the cloud, and it is available for us to use with a single line of code and get that resources in your hand, pay as you go model, not to shell money upfront and build like expensive data center. So that is the beauty of quantum chemistry coupled with the cloud, where the solution have a niche. And somebody was saying like how to get faster solution, simpler solution, cheaper solution. You always pick two, but now cloud sometimes changes this equation where you can have, faster solution. You can have a better solution with the algorithm like this, and a hopefully cheaper solution. And but in all, like out of those three, mostly people miss, which Valentin kind of like mentioned, the accuracy. So accuracy on this experiment is very, very vital when you formulate any drug or you want to, have any new material found. So we always leave accuracy aside. Accuracy is the most important in my mind.
Awesome. I think we also have another question on the chat. One of the use cases in the past is a toxicity prediction using software in the pharma. Are you guys involved with this approach? Can I use QEMIST to this today?
Oh, that's a good question. Yeah, good question. I'm familiar with toxicity prediction. It's very important for creating new drugs and compounds we're putting in our body. Right now, this is not available with QEMIST Cloud. If you want to hear about upcoming features that are going to be released, I would highly encourage you guys to join our mailing list or follow us on social media. Here you'll get the most up-to-date information about what we have slated for release and when our next feature releases are.
Yeah, right now we're predicting some more essential properties, starting with ground state energy, moving on to excited states, moving on to geometry optimization and everything. And gradually we'll build the capability to predict more and more interesting properties as we move forward. So stay in touch if you want to be on top of things.
Before we continue, if anyone has joined new to the show, welcome everyone. We have good chemistry on the call today. We are just seeing the chemist demo right now. If you have any questions, please feel free to pop them on the chat and we'll try to get them answered from the good chemistry experts here. You can continue, Nicole and Valentin.
All right, thank you for the reintroduction. I guess I can go back to my notebook and finish our demo here. So where we left off, we had initialized the client, we defined our molecule object using greeted coordinates, then we've defined the solvers we want to use, the algorithms we want to use to solve the electronic structure solver, and then we've sent the problem to our QEMIST Cloud server. And how we track problems in QEMIST Cloud is we give each one a unique integer ID. We call it our problem handle. And this problem handle is just an identifier for a problem. You can use it to pull results later. You can use it to track its progress on the cloud, and you can see it on the dashboard.
Nice.
So let's go back over to our QEMIST Cloud screen, and we were in the Howdy project. And we should see
our handle here.
Pardon me?
So that handle is that workflow item which you created. We should be seeing it here.
Yes.
Yeah. So it's kind of like an executive management dashboard too, like multiple research scientists have their own Jupyter notebook, they're submitting the experiment, and then they have a login here, they can see the task, track what is happening, and things like that. Right? Mm-hmm. Great.
Yes, precisely.
Can our users try out the QEMIST Cloud?
Sorry?
Can our users try out the QEMIST Cloud solution that you're showing us today?
Yeah, absolutely. As I mentioned earlier, for you guys just joining, then after the demo, we'll drop a link in the chat. You guys can follow that link and sign up for an account. And when you sign up using that link, then we'll give you $10 worth of free credits to use to play around with our platform.
Yeah, and then the homework for the people are, they should create a beautiful hydrogen molecule, the basic one, and put it on the LinkedIn and saying like how easy it is to create a hydrogen molecule formulation with the QEMIST Cloud, so that the others can also leverage the benefit.
Yeah, and another easy molecule to create, you can see here, our beautiful butane molecule. This has been solved. You can see the solve time was exactly a minute, actually. And you know how I was talking about using decomposition to break a large problem into manageable subproblems? That's what this subproblems is here. So in this case, we broke this one molecule into 13 unique subproblems and solved those. I graded the results at the end. And at a cost of only 34 cents, we have our ground state energy for this. How you retrieve those results, you can do those through the dashboard, but as a developer, my preferred way to access your results would be using this ID and our client library. Let's pop back over here to our notebook. So as you can see here, we've got our get result call that will pull your data for that problem back from the cloud. And how we deliver results in the client library is in a Python library, or in a Python dictionary rather. So it's very easy to then take the output of QEMIST Cloud and programmatically feed that into post-processing. You could put it into graphical software. You could pull out properties and feed those into other scripts. So in this case, I'm just pulling out the total energy and the solve time, as you can see here.
Awesome.
Everyone good so far?
Yeah, I think we have some more questions. No namesake is coming in with some really great questions. So I think he asked, with the trial, like what can we do with $10? I think, Nicole, you just mentioned like you could solve, I already forgot what the top one was, but for like 34 cents. Like, yeah. So that is, that's wild. And then the other one was, can I see other people's work? So you mentioned like workspaces. Is there like a collaborative aspect if there's like a team that's working on this together?
Yeah, absolutely. So can I see other people's work? You as a user signing up for a personal account using the link, you would not be able to see anyone else's work on the cloud for obvious reasons, IP and the like. But if let's say you were a team working on a project together, then you could create a project and add collaborators. So you could all submit molecules to that project, see molecules others have submitted, and even have a shared credit pool for your organization.
Awesome. Cool. Thank you.
Coming to the cost, is there a way by which we can see how much it would cost us if, let's say, we use one algorithm versus the other? Is there a way where we can analyze the future costs that it would cost us?
Yeah, absolutely. So that's a great question. And let me see if I can show you one here. So in our client library, we actually include a function where you can predict how much a simulation may cost before actually running it. It's called check problem cost. I don't actually have a script ready with it here, but this just gives you an estimate of how much it would cost to run a molecule, and you could play with parameters before you run something that would break your bank.
Awesome.
Any other questions?
A little off topic, but do you have or Nicole and Valentin, do you have like a favorite molecule and why? Anyone that's like super fun and like reactive for some reason?
I don't have a particular one of interest, but I keep hearing people bringing back caffeine as a molecule of choice for fun examples. So maybe I'll defer to caffeine because I can read
that. You read my mind, Valentin. Caffeine is one of my favorite molecules as well.
for good reason. I think definitely mine too.
Another interesting example of a molecule, if you go back to that blog with AWS, Good Chemistry, looking at environmental pollutants, that whole class of molecules, the PFAS molecules, they're interesting because they're meant to be very inert, very non-reactive. Think of like the non-stick coating on your pan, very inert, but because of that, they're very difficult to break down. So our whole study was about how these molecules can be broken down when they become environmental pollutants.
Yeah.
I think there's a question from Quantitient here. What kind of startup delays are you experiencing when launching a job requiring thousands of calls? Well, I think there may be a graph in that link that just flashed the blog post for 1 million calls. Otherwise, for smaller jobs, Nicole, do you have any idea of what kind of startup lag you experienced at the beginning?
I can't give you exact numbers for that one, Valentin. I think if you're looking for hard numbers, then the blog post is a great resource to go to. But obviously, this is a challenging problem, and we'll see some startup delays. But with tuning and with the kind of scaling we're working with, we've tried to minimize those on our platform.
I think a part of it is also dictated by the availability of resources in the cloud as well. At the end of the day, if everyone is using the cloud, it's not like we can just kick them out and just launch all the computers we want instantly. I think we allocate a number of resources, and that number of resources tends to grow with time to meet the needs of the application.
Yeah, this blog which is flashing right now screen, that gives some benchmark. Yeah. So Nicole, what else we are seeing?
Awesome.
Are we talking about Tangelo at all today?
Yes, we are. I'll close this off with one quick example of just another thing that QEMIST Cloud is capable of. So here we took our butane, we solved it using our highly accurate IFCI method, and in a minute we were able to get the total energy. Sorry, what was that?
I was like, yeah, 60 seconds and nice.
Solved. Great. So now what we're going to do is just run the same molecule through a machine learning enabled solver. So you'll recall that QEMIST Cloud also uses machine learning based solvers to accelerate calculations. So here I'm just defining one of those solvers, the ANI or ANI2X. This was actually developed by one of our scientific advisors, Adrian Reitberg in the Reitberg group. So we're defining that solver. We're giving it the same molecule as before, submitting it, and then we're getting the results. And as you can see, once again, this is a small molecule, but you can already see the order of magnitude speed up that we have using this solver, the total energy and the solve time in only 4 seconds. Just a quick aside to this is this machine learning solver is actually trained to a different level of accuracy. So it's trained on data using a less accurate algorithm than the algorithm we're using up here. So the differences in the energy are because the solver itself is not trained to be as accurate. And that's part of what we're doing with QEMIST Cloud is to improve and make these algorithms more accurate. So eventually you'll have full CI level accuracy on a very fast machine learning solver.
So essentially we are reusing these very scalable simulation methods to compute with unprecedented accuracy energy on bigger system, and then re-injecting that into the machine learning models to kind of like level them up.
Mm-hmm.
Can the users use their own models, or is it compatible with just a certain set of models that is proposed by Good Chemistry?
Currently, by models, I'm assuming that you're meaning solvers to solve the Schrodinger equation, the electronic structure solver equation. Currently, we don't support user-defined models. Users can choose from different levels of theory and different models that we have available on our platform.
Okay.
I think we are still thinking about how maybe companies in the future could come with their own data, though, to train these models, because a lot of companies are a bit secretive about the research, about what they're working on. And it would make sense for them to train or kind of customize this model based on what they have, right? So there's some customizability here in mind, but it's a bit early to say anything.
Mm-hmm.
And you were talking something about Tangelo. What is that?
Ooh, okay. So I guess we're diving into the quantum computing part. I would like to take a step back here and first just talk about quantum computing. If you don't mind sharing my screen, we'll take this at a time, because it's going to be a bit wild. So
we love
this is the part where I try to vaguely explain what quantum computing is in 2 minutes, and it's of course not going to be great. So please be kind to myself. Please be kind to yourself, who's going to be at the receiving end of that. Honestly, you don't need to have a profound understanding of quantum computing at all to understand the story that I'm going to talk about with Tangelo and trying to apply this to quantum chemistry. So I'm going to go back and forth, left and right, between classical and quantum to try to give you a little high-level breakdown of the differences. Classical computers. The data is stored in bits of information, and these bits can only be in two possible states, in either a state we call 0 or a state called 1. On the technologies today, after decades of innovation, it's all about transistors and current going through wires. That's how we implemented that object. On quantum computers, well, it's already a bit wild. The data is stored in quantum bits that we call qubits for short. Qubits can actually store an infinity of superposition of states between 0 and 1. So a qubit is at the same time 0 with a given probability and 1 with a complementary probability. You see a little drawing, that's the block sphere. That's just a nice geometrical way of perceiving the states of a qubit. Any point of the surface on that sphere represents a superposition of a 0 and 1. Calculations are deterministic on a classical computer. Tongue-in-cheek, 2 + 2 = 4, easy peasy. On a quantum computers, it's probabilistic. You're creating essentially superpositions of one or several qubits, and at the end of the day, you create a probability distribution. For example, I give you a little histogram. It has like 50% chance of being 0, 50% chance of being 1. You can imagine that I'm holding a coin in the air vertically, and you don't know if it's going to land on heads or lands on tail. But when I actually want to get the answer out of my quantum computer, I don't get this entire probability distribution. I only see that it's heads or tail. So if I want to get an idea of what these probabilities were, well, I have to repeat this many, many times to count the heads and tails, and eventually the law of large numbers tells me that this should get closer to the probability. The operations in the classical computers, they're defined by Boolean algebra. We manipulate 0 and 1, true and false, and here you go, 2 + 2 = 4 again, but with bits. Hopefully I didn't make any mistakes with that. It would be impressive. The quantum computing side, where it's a bit wild. You can see a little bit of the drawing in the middle. Well, that's how we represent the quantum circuits. The horizontal line at the top is the first qubit. Bottom one is the second qubit. They both start in state 0, so the system is in state 0, 0. And the operation we apply is actually linear algebra in Hilbert spaces, which is a fancy way to say we apply matrix operations that have special property. In particular, if you just focus on the top line and just that H gate here, it's called a quantum gate, this operation, that would put my first qubit in that coin toss situation where it's in equal probability 0 and 1. And if I put on this second qubit and I look at this second operation here, it's what we call the controlled NOT operation. What that thing does is basically, if the first qubit at the top is in state 0, then we flip the value of the second qubit, so it would become 1. It would stay 0. Never mind. If the value of the top one is 0, then the value of the bottom one is unchanged. If the state of my qubit on the top is 1, then we flip the state of the bottom one, and it becomes 1. So at the end of the day, you're manipulating these two qubits at the same time, but at the end, you can only observe two different states. Either it's 0, 0, and in that case, there's no qubit flipping on the second operation, or there is flipping, and in that case, you observe 1, 1. So it's kind of wild. Like the first gate here, the H1 is what enable a qubit to be in a superposition, and the second gate, this controlled NOT gate, is what allows entanglement. The values of these two qubits are now linked to each other. To wrap it up, classical computers is a mature technology. You can use bits for quadrillions of operations, and that's fine. You get a result at the end, very low probability of error in there with, wrangling your bits around. quantum computers, unfortunately, nascent technology for now. These quantum gate, these operations, they're not perfectly executed. Instead of getting these exact probability distributions that you're expecting, you get slightly different ones because we're still tweaking and perfectioning these quantum computers. As you can imagine, well, this error accumulates as we perform more and more operations, and at some point, well, we kind of have like numbers that don't really mean anything anymore. So in that sense, we are limited. That was my attempt at. I think I spent 4 minutes on this.
Great.
Of
Great. Yeah, great.
I don't have a
Explaining difficult
PhD
topic.
in quantum information science. It's okay if you have limited understanding. I actually do too. I would argue most experts also feel like they have a reasonable knowledge, but not full about this. But I just wanted to give you that context. Maybe an interesting question is, okay, why am I talking to you about quantum computing when we're talking about chemistry? Why? And there's actually a good reason why we're looking into it, is because when we look at quantum chemistry simulations, a lot of the accuracy comes from small particles, like electrons, for example. And these particles follow the strange laws of quantum physics, like they are in a superpositions, they are entangled to each other. A quantum computer is basically a device that tries to harness the laws of quantum physics to make some computation. So then it makes sense to try to encode things like particles and the simulation of molecules into a machine that can leverage these principles to do computation. So that's kind of like the gist of it. We just hope that essentially we have a more natural way to express these problems that should bring down the consumption of computational resources back from something that's exponential and grows too fast in classical computers to something that's hopefully closer to polynomial. But right now, quantum devices are still very young. They accumulate error pretty fast. But also quantum algorithm development is in early stages. We don't have a lot of different algorithms. They don't seem necessarily very good in terms of accuracy or in terms of the amount of operations we can do. So that's the context where we're starting from here right now. We just need to do a lot of research in order to finally do something interesting with a quantum computer for chemistry.
We have a question on the chat. What are the practical applications of quantum computers? How much money has gone into their research? And is there a single thing they have been used for or can be used for? If yes, what specifically? Also, can they be scaled up like modern computers?
Okay, I'll do my best in a nutshell. I think the most answer to what can we do with, I mean, it's 4 questions, that's fine. What are the practical applications of quantum computer? The most honest answer is we don't know, because it could be a lot of stuff, but we need to find how we can express our problems in the crazy world of quantum qubits information. However, some fields of application that have like demonstrated potential are optimization, for example, cryptography. A lot of people are talking about cryptography, factoring numbers and breaking the encryption and bringing the world down. Chemistry is one of them, but also the fields like finances and such are looking into it. We may be able to solve some very fundamental mathematical problem with a quantum computer, which would make them, it's applicable to a larger collection. There's a lot of research that's going into that. Lots of companies, big companies, smaller companies like us, for example. There's a lot of money funded by the government for the international, essentially, programs as well.
Yeah.
And can they be scaled like modern computers? They can be used in conjunction with anything else we have today, CPUs, GPUs, and people have already started to think about how could I use an army of computers to solve problems.
Yeah. So I think just to add on the practical side of the application, I think I have a different take on this question. I want to reformulate the question itself. Okay. The case is here. Do we have a do we have number of qubits, size of the qubits, which can solve a practical use case in coming year or coming decade? We don't know that. That lot depend upon the hardware providers who are working on getting a first quantum computer which has advantage over the classical computer in terms of the number of the qubits which can support. But rough idea which we all from the quantum community say, you almost need 1 million qubit to have some sort of advantage on some specific algorithm, on some specific problem when you compare quantum with the classical. An example would be like on the cryptography, there is a famous debate going on, can quantum computer break the RSA encryption? On a theory, there is no doubt. It has been proven on a theory, like it will be. The question is when. Now, as a software company or as a compiler below the software, or what you will be doing during this time when hardware providers are working in their lab and increasing their qubit count every year. Do you want to wait till you get 1 million qubit and then start sequentially? Or you as a startup or you as a company who want to work in the software side want to start with a toy problem now, expand slowly as the qubits are increasing over the year, and be ready to make revenue on your algorithm, which is your IP, which you're working right now. I think it's a no-brainer. You should be starting now so that you can reap the benefit if quantum computers are available whenever they are available. So you don't want to be in a sequential manner, right? Hardware is there, then software engineers or software developers of the world, companies of the world are then thinking like what application I need to build. So there are elaborate level of the application which can be built, right? On the quantum cryptography side, on the simulation side, which we are talking about quantum hydrogen molecule or any other butane and all. But there is another set of application which is called as optimization, which is very relevant in the world of logistic and supply chain, where you want to have or a last mile delivery of the package, right? Like all of those can be done with a technique called as annealing, with a different type of quantum computer, like Fujitsu digital annealer or the D-Wave, which is a little bit more mature in my mind, but you can actually do some of the optimization problem there, right? And apart from that, like there is a close synergy between how you do the machine learning, right? You define the parameters and then you feed it with algorithm, you train it, then you test, validate, it goes in a circular loop. I think where we will see in next few years the biggest return of our investment is this hybrid type of system, and the quantum machine learning, which is closely related to the quantum chemistry on the variational quantum eigensolver, right, where you have a pre-processing and post-processing, pre-processing defining your parameter, and then the ansatz, and then you get the output from the computer. You will have some classical optimizer to have the most optimum parameter. So, in my humble opinion, I think it's a very valid question, but the question should be rethought, and that rethought should be: do I want to wait until all the qubits, which is kind of like a million qubit, available? Should I do it now? So I think answer lies somewhere in between, right? If I'm an investor, I will invest and take that risk, and that is what companies like Good Chemistry or other quantum startups are doing. So I think I tried answering the question. There is no easy answer, but that is my take on that.
Thank you. I think the word practical was important here, is that first, it has to work, it has to solve your problem. For that, you require a machine that has the capability to run your problem, let's say enough memory, and can apply the operation, gets you your accuracy. And I think the second part of this is, yes, but somehow it has to be better or more interesting than what I could do with classical computers. Otherwise, well, that's cool. You can do something that we could already do. I think really the bar here is different for every single field of application and by use case. It depends on our ability right now to find good algorithms that are going to get to the solution accurately and with less resources, and also developing these computers so that they are competent enough to handle these algorithms. And when both of these things meet, then suddenly you have a practical application. But this is a very interdisciplinary research effort at the moment.
Yeah, it's an active area of research. All right, another data point around this, like why quantum matters, is like, see, if this last year's Nobel Physics Prize was for quantum, right? And those individual researchers worked independently from last, I don't know, 30, 40 years. And quantum is not a new phenomenon. It was always there for last 100 years. We are seeing a lot of press today because there is some good work which was done in last 15 or 20 years, because a lot of startups are working on their core intellectual property, kind of like an algorithm, but then hyperscalers like AWS are providing that technology so that you can easily experiment. So something is working, which is making this. We are making noise in this field right now. A lot of press is around that, but of course, like, to have a pure advantage on experimental side of the house, we are still a little bit far, because we don't have the qubit and there are noise and all that decoherence. We can go and talk about that, but right now you don't have that qubit numbers available to satisfy the pure advantage. But it do exist on paper. Some of the algorithms, Grover or Shor's algorithm for the cryptography, they have shown on paper that have been peer reviewed by many people, without doubt, like, yes, when quantum computer will be available, some of the advantage which we are talking on the papers will be visible. Classical RSA encryption will be broken when we reach a certain level and maturity in terms of qubit number. This was very important question, so I took little time in explaining this. But without further delay, let's get back to the Tangelo, Valentin.
Yeah. Awesome. Thanks, Ravinder. Yeah, definitely to no namesake's comment point. So, Val is just talking about giving the overview of quantum computers before we talked, and kind of went in through the application of quantum computers as it relates to good chemistry. But, obviously there's a ton of topics and things we can talk about when it comes to quantum computing. So I did send in Perminder's LinkedIn in the chat. So if you want to talk, quantum computing, he's definitely there. Feel free to reach out. But Valentin, I'll let you continue on.
Okay, thanks. With that context set, that we still have a lot of research and stuff to do. Basically, because quantum technologies are not quite there yet and applicable to chemistry right now, we have decided to look into this through an open source package called Tangelo. So it's a Python open source package that has a project on GitHub. I'll go through that, on a very permissive license right now, to take quantum chemistry workflows on quantum computers. Right now, we don't really have, systematic approach in algorithm when you can just say, hey, here's a molecule, I just throw it at the algorithm and the algorithm gives me a solution. Right now, if we want to actually do something that's feasible on the current quantum devices we have or on simulators, we have to be a bit smarter than that and take more steps. From left to right on this diagram here, I would start with defining a molecule like Nicole would do, for example, XYZ coordinates. I could optionally try to apply some problem decomposition technique to chop this problem down into smaller problems. Tangelo has problem decomposition techniques, but otherwise we could integrate with some techniques in QEMIST Cloud. You pick a quantum algorithm. There are a few that the research community have found for different purposes. It's a sequence of instruction that encodes the problem into qubits and eventually, builds a number of quantum circuits that needs to be executed on a device. Eventually, on the right, well, you can send this problem to a simulator or quantum computers. Quantum computers are available today, not widely available, but for example, Amazon Bracket is a fully managed quantum computing service you can use in order to submit experiments on some hardware developed by different companies. Mm-hmm. And you take the results out of these quantum devices, remember, computation is unfortunately not perfect. And then you decide what to do with it. Can you reconstruct a quantity that has meaning for the chemist because you're taking a histogram and you have to somehow make numbers out of it? And can you find interesting way to correct or anticipate the error that comes out of your quantum computer because maybe of insights from the chemist or Jamino? So some general, what we call error mitigation techniques. And maybe you have to repeat that a number of times until you get to a final solution as dictated by your algorithm, which could be iterative or just require many circuits to be submitted. Long story short, well, it's actually complicated right now to study what we can do. And we really need tools to help people try new things, try new algorithms, try to change different options, try to add different building blocks to build a workflow to reach a conclusion and learn from quantum devices or algorithms in general. So Tangelo can be used by itself. It's a real project available on GitHub. Probably someone will post the link, but under the Good Chemistry repo, we have Tangelo with a lot of documentation. You'll find the same figure. It has been used for a number of publications, and it's going to grow. There's going to be more and more publication in the field of chemistry relying on Tangelo this year. You'll see us also at a couple conferences and stuff like that making speech. There's another repository that has, I'm going to go back a window here. There you go. That's dedicated to examples. We like notebooks because quantum computing is complicated, software development is complicated, and quantum chemistry is also complicated. So if you're interested in diving into it, well, there's a number of things that exist out there. And if you have one or two questions, we can dig into that. Otherwise, I can show you a demo that actually may answer like quite a few of your questions.
Mm-hmm. On a side note, who came up with this word Tangelo? Was it you, Valentin, or someone else in Good Chemistry?
I'm sorry, can you repeat that?
Either it was you who coined this term Tangelo for this product, or someone
Yeah,
else?
yeah. Like the name, the logo, pretty much everything. The only thing I don't take credit for are the really cool algorithms and the chemistry in there. That's the researchers. Clearly. And you're right, Tangelo is a fruit. A Tangelo is actually a mix of a tangerine and a pomelo. Tangelos are in season, I think, between December and April. So maybe if I run down the street right now, I could find some Tangelos. They're pretty good. All right. Shall we move on to a little demo there? Yeah, I think yes. the hype is real, but let's see something more real. Okay. I'll take you through a quick little notebook. It's not going to dive into super depth on the chemistry parts. Like I can rise the surface and give you a sense of that, but we're not going to go too far. I pre-run this cell. This is just setting up environment. What you can notice is just that I went and installed Tangelo from the GitHub repo with the develop branch because that's the most up-to-date. And I've installed the QEMIST Cloud client library because I want to demo a little feature that uses QEMIST Cloud and Tangelo together. Right. A little bit about quantum circuit. Well, we talked about gates and circuits earlier. I want to give you a sense. So Tangelo has simple classes, gate and circuit. A gate has a name. Usually it has some indices that corresponds to the qubits it's going to touch on. And sometimes it has additional parameters, such as a parameter like an angle for a rotation gate, for example, or a control one. So if you remember that drawing earlier, well, these two gates are the ones that were here. There, the H gate on qubit 0 and the control node gate on qubits 0 and 1 and have a little rotation here. When I just pass this list of gates to make a circuit out of it and draw it, this is what I can see. I have my H gate, my C node gate, and a rotation with angle 3. 3 is a bit less than pi, so as you can see, that kind of translates here. We can simulate this quantum circuit, not run on a quantum computer, but right now just on my laptop. We can simulate it. I just call a backend simulator here, and I can just call the simulate method. I pass my circuit, and I'm going to ask for it to return the state vector. I'll explain what that is in a moment. So earlier I showed you that, what you get out of a quantum computer is like a histogram. Well, here's an example. I have a 2-qubit circuit, so I have a histogram of 4 different bit strings, all the combinations here of, what my 2 different qubits could be. That's what I can get out of a quantum computer. This state vector thingy at the bottom are all the magic complex numbers that give me the probability distribution. It's a simulator, so I can cheat. I have access to it. On a real quantum computers, I do not. What actually happens when you run things on a real quantum computer is that this guy, we don't get it, forget about it, is that I told you earlier, we get kind of like a probability distribution with my coin toss heads or tail, but at the end you only see heads or tail, and I would have to repeat this many times and count the heads and the tail to get an idea of what the probability of getting head or tail is. Well, that's the idea here. We call that taking shots. If I run the same simulator of a cell circuit with a number of shots, and I say I'm gonna repeat that 1,000 times, I get a histogram. I observe, a number of bit string in all different. And every time I run this, I will get something that is slightly different. Is it the same every time? No, there you go. The numbers have changed again. Sometimes I may not, for example, see 1, 1 and 0, 0 at all. They seem to have a very low probability. So this is closer to how a quantum computer works. And then, I would take this histogram and I would apply complicated and magic formulas to make numbers out of this that chemically mean something. Right now, what we can do is that we could send this to Amazon Braket, which is the fully managed quantum computing service. And we're going to use QEMIST Cloud as an intermediary, essentially as an integration. So even if you don't have an Amazon account, for example, if you have QEMIST Cloud credits, which you can sign up for with the links Nicole given to, you could submit an experiment on a quantum computer or a simulator. So I would essentially plug in my authentication token. Yeah, it's cropped, so you can't see the end. It's a demo account anyway, so it will be good. And I would create a connection object. Just like Nicole, well, I want to know an estimate of what it's going to cost to submit this circuit for 1,000 shots. And Amazon here has a selection of simulator, but also devices. For example, there's a company called IonQ that has made a quantum device, and that would cost you $10 to run with them. Or someone else from a company called Rigetti, well, this would cost only 65 cents. Different devices, different people, different prices. You can learn more about Braket at the link at the bottom of the chat. Today, I'm not going to submit something on a quantum computer. Quantum computers are scarce resources. There are not many around. If I submitted something right now, I would have to get in line. There's probably a bunch of people waiting for their jobs to execute. So in order to, you can do that on your own, right, using credits. That is completely fine. For me, I'm just going to use a simulator called SV1. So it's going to go through QEMIST Cloud. QEMIST Cloud is going to submit to Braket. And I'm going to get a job ID out of it. And I'm going to ask to get for the result. So it's going to make me wait a little bit. In the meantime, if I go on my dashboard and I refresh my demo project, I can see that there's a problem in progress, right? 1,000 shots. So most likely it is my problem. I'm gonna refresh maybe once or twice. I think usually within a minute it gets to complete, but I would get the answer from Braket. Awkward moment live. Okay, my problem is complete. So in the QEMIST Cloud dashboard, actually, I can see everything that Braket would give me. Measurement probabilities are the numbers that would get into my frequencies. Because it's very experimental and everything, there's a lot of details about essentially how the computation went, what happened, like how my quantum circuit was compiled and everything. This is important for researchers. For us, it's a bit complicated, but there's a lot more information in there. And yes, my cell has completed in my notebook, and these are the same numbers as you just saw through the dashboard. So long story short, it is possible to build quantum circuit to simulate them on your laptop up to a certain size, and also submit them to quantum devices online today. That kind of closes what I wanted to show you about quantum computing to give you a better grasp on it. But I want to go back to chemistry to show you what's really happening now, the reality that we are facing.
Do we have a blog, Valentin, about Tangelo yet?
No, that's a great question. There is actually a blog that should be released within days on the quantum blog post. We have shown an experiment with Tangelo on real quantum devices to study, for example, the umbrella effect on a small molecule called hydronium. So that I will give you a sense of how we can combine all of these toolboxes essentially here and all these functions, these classes to run experiments today that are pretty complex. So stay tuned, maybe follow us on LinkedIn or something like that, or sign up for the mailing list. Then you will know immediately when it's out. All right, I was talking about quantum algorithms earlier. I'm going to give you a short example. So right now we can't do a lot of operations on quantum computers because we accumulate some error, and eventually, well, you get stuff that it's not very meaningful. So people have been thinking really hard, and they came up with an algorithm called the variational quantum eigensolver, but we'll call it VQA because that's cuter and shorter. The idea is that people look at the molecule and they encode it into qubits. There are several methods for that, but you get what we call the qubit Hamiltonian H here. And then the idea is that using something called the variational principle in chemistry, we could decide to have a circuit. The choice of circuit can be pretty arbitrary, and have gates that have parameters, for example, rotations that have angles. And we are going to use these angles as degrees of freedom. By changing the values of this angle, we get a different energy that comes out. And we're going to use a classical optimizer to try to tweak and move the values of this angle to decrease that energy and eventually get to a loss one. So we have a classical optimization loop where we are running circuits that are slightly different by tweaking some angles until we get the lowest number that the optimizer can find, and we declare it the VQE energy. And that's as far as I'm going to go into it because that's freaking complicated. I just wanted to give you a sense that this compromise, we're trying to ask the classical computer with classical optimization to do more work so that the quantum computer has less work to do. The idea here is that this quantum circuit, we're trying to find ways to design quantum circuits that are short, like require less resources, less qubits, less gates, while somehow retaining as much accuracy as possible. So there's a wide range of approach where we have accurate circuits that are like ridiculously big, and we can't do them right now. Or we have circuits that are very, very simple, but unfortunately the accuracy is all over the place.
Yeah. So this is where I think there's a beautiful figure, beautiful explanation, Valentin. This is where it has a little bit of resemblance on the classical machine learning side, right? The setting of the parameter, which is the theta, putting it into the algorithm, which is your energy evolution, measuring it, take it out, to see like whether you need to optimize the parameter. You use optimizer, you repeat, rinse it, repeat it, rinse, repeat until you get a most lowest energy, and that parameter is the parameters which you are going after.
This is a beautiful analogy. This is exactly that. We have a model, except that model at the end of the day is a quantum circuit, and we're trying to find the right weights for this quantum circuit somehow. Except that we're not here building a model that can predict for many, many molecules. We're just trying to solve the problem for one molecule. Yeah.
Yes, of course. And then Nicole said like the energy, ground state, right? So ground state is the lowest energy which you are interested in finding because that is the most stable state a molecule would be. That would be where its natural state is. That is where you will have the bonding and other things.
Yeah.
So say I'm little bit now comfortable with chemistry. I said like in the beginning, I'm trying to remember my high school chemistry, but I think people on the call are also getting a little bit knowledgeable with these beautiful platforms which you guys have built.
I work with a bunch of PhDs in chemistry, so my answer is always, I know nothing.
Oh yeah, they are the
carrot stuff. But now let's get back to chemistry and quantum computers, try to like put that together. It's a rather simple system. It's just 10 atoms of hydrogen disposed in a circle, separated by a given distance here. There's a list of coordinates, just like we saw earlier. That's it. They all sit in the same plane. They form a ring. Now I can make this a proper molecule object. So similar to what Nicole showed us earlier, Tangelo has a molecule object. And, we look at the position of these atoms, and then we know how many electrons are there. We know how many atoms are there. We have an idea of where these electrons could be in what we call the orbitals. We compute a number of pretty simple, let's say, energies in calculation. So now we have a molecule object that has properties. There's some warnings here, probably some deprecated packages because I'm using an advanced version of Python. Tangelo provides you access to classical algorithms. Why? Well, because you're going to get an answer out of quantum algorithms, but it's an area of research. Sometimes you're not quite sure where the quantum algorithm is going to take you. So you want to get an idea, okay, how does it compare to the exact answer or like a reasonably good answer? So we provide two algorithms, FCI and CCSD. FCI is the exact one that unfortunately cannot scale up to large molecules. CCSD is a less accurate one that scales a bit better as a result. These run instantly. Like this is a very easy problem for my laptop, for our classical algorithms here. Boom, I got the FCI energy that's over there. CCSD, again, approximation slightly different. Now, is this an easy problem for a quantum computer? Well, here you go. I'm gonna run my VQ algorithm. I import it, and I just pass it my molecules and very straightforward options. Like it's an ansatz that's built from the molecule called UCCSD, kind of like the generic thing that everyone tries in the field that's accurate. And the qubit mapping everyone in the field knows, again, called Jordan-Wigner. So the way we encode qubits, the way we encode the molecule into qubits. And if I just go ahead and say, yeah, that's fine, let's just run that. So first, I'm not running the algorithm here. I'm just asking, can you please build the underlying object? And can you please give me an idea of the resources it takes? Because I'm not even sure my laptop can run this. What do we find? We find that we have a very deep quantum circuits with about 32,000 layers of consecutive gates. So right now, to give you an idea, a quantum computer can maybe do a few dozens of them to the accuracy that we're hoping for in chemistry. Beyond that, it's not really working. So we're far away from that. And that would require about 20 qubits. We say with classical optimization, well, we have apparently 350 parameters to optimize that direction. So that would be a lot of quantum circuits to like run essentially and everything. So right now, this is really unappealing, and a quantum computer could not run this algorithm. So we get back to the idea of problem decomposition and say, can I chop this problem down to have smaller problems that would require overall, less resources to solve? And instead of solving my big problem, I solve a collection of smaller ones. We have another technique here that's called DMET that is an example of how you can achieve that. Essentially, I would say, well, now I don't want to have a single molecule. I want to chop it into fragments of one atom each, so 10 fragments of one atom. I want to use that VQ algorithm to just look at one of these fragments. For the other 9, I don't really care. Actually, it's a ring. It's very symmetrical. The fragments are all the same. Like, right, what I'm going to get for one fragment is the same that's happened with all the other fragments. So I want to get that out of the way. And here I can pass different options to VQ. There's a lot of degrees of freedom. For example, I'm choosing a different qubit encoding here and the same ansatz. And I'm doing the same here. I'm trying to build my solver, and I want to get an idea of what the resources are. The numbers we see are very different. That choice of approach is dramatically different. Right now, we only have 14 layers of consecutive gates. That seems actually much closer to what devices can do. We only need 2 qubits, and there's only 2 parameters in the entire algorithm to figure out to solve one fragment. So it seems that it's much more doable. You can have here a beautiful description of what these bath and fragment orbitals are for the chemist here, but I'm not a chemist, I'm not going to talk about it. It looks feasible, but let's simulate this on my laptop, but it's small enough to be simulated now. Is it going to be accurate? Apparently, the accuracy is like not as much as we would like to be for a practical application, but it's not bad. It's 8 to the power 3. So it's, reasonable, even though you may be lacking context. So on the one side, I'm trying to build an approach that's going to be feasible for my laptop, or if I can, a quantum computer. On the other side, I always try to keep track about the accuracy. Yes, but is this likely to work or not? And starting from there, it's really make your own adventure. This is an area of research. You want to compute the energy of this fragment, you can retrieve this circuit that corresponds to this fragment here, and you can retrieve the qubit operator that corresponds to it. But from there on, you're going to have to draw through the many toolboxes to try to reduce the computational requirements as much as you can, find good algorithms to go about it, look at the accuracy, maybe take some results out of some hardware and try to correct the result and compute your quantity at the end. How we should go about this right now is an open question and involves many challenges that have nothing to do with quantum computing or chemistry. Like, there's some stuff here that can be solved with optimization, with graph theory, with you name it. So regardless of your interest in your experience, you may actually somehow contribute to get people closer to using quantum computers for quantum chemistry. And I'm going to wrap it up here with this demo, with these nice words.
Awesome. Thank you so much, Valentin. So how would our users start using your solution or the QEMIST Cloud or Tangelo?
All right. Well, anyone can install the package with pip go on GitHub, to start forking, download this. If you can give me a little star, for example, to just help us boost our visibility, that would already be nice. Otherwise, well, if you sign up for an account on QEMIST Cloud and you install the client library and Tangelo, then you can repeat anything that I've just shown you right now. This particular notebook I've shown is extremely simple for this demo, but we have actually a broad range of notebooks that go a bit more in depth on the Tangelo example repo that you are free to run, and some of them involve or replicate experiments on the cloud.
Awesome. Yeah, also, I think the links are there in the chat. I'm also pasting it here. Okay, Art has already pasted them on the chat, so please feel free to register there or look at the Tangelo examples.
Here's a couple links at the screen for some of you that want a little recap. Feel free to sign up for updates on our mailing list, follow us on social media. We have a presence on LinkedIn. We have a presence on Twitter as well. That's the best way to stay abreast of, new releases with Tangelo and everything. For Tangelo, what's really important is that we're trying to build a community around this. We have tried to create tools to really empower researchers to build a spaceship to take us to the moon, and it's gonna take time. It's gonna take a lot of people to get there. So if you can reblog or just talk about this to help us with visibility, that would be tremendous. And then some researchers or some people we don't even expect are going to come up with crazy things, and eventually maybe we'll be able to do some quantum chemistry on quantum computers.
Yeah.
Awesome, team. So I posted a bunch of links in the chat. No namesakes, continuing with some awesome questions. So Valentin, maybe, or Nicole, as a company in deep tech and a niche field, what are your biggest challenges? Loaded question.
$1 billion question. It's a
Yeah.
$1 billion
Oh
question.
my gosh.
Let me ask my CEO. Let me see.
Well, I think something I can say to that, working on the solution, is when you're on the cutting edge of technology, then you're solving new problems. There aren't a lot of resources for tackling the issues we're facing. So our biggest challenges, one of the biggest challenges I've seen from an engineering perspective is like the lack of resources available when working with new technology and really having to solve our own problems.
Yeah, I think what I take away from Nicole said in particular, as someone who works with researchers, is that we are reading papers, we are looking for innovation, we're looking for new things every day, and the best way to write software that are gonna implement these methods. What's challenging is that we need to be innovative, and a lot of people are probably looking into the same problem. You have to stay on top somehow of the state of the art and try to roll that out to something crazy on quantum computers or on CPUs and GPUs in the cloud. So we have to work with a lot of people that have really different backgrounds and also that have to figure out how to solve tough problems that no one has really solved before. I think for me, that's what's both challenging but also the most exciting part of this.
Yeah. Just to add to what you guys are saying, like it's an interesting time to be working in the field, and it will take probably an entire community, and the community is the right word you use, because you need the research scientists who are actively experimenting
Yeah.
in the lab, but at the same time, linking that to the resource problem, we need to also inspire our high schoolers and the undergrad to take up this subject, who will come and help in few years in building of the hardware, and some of them will go to the compiler or the software side of the house, and the industry itself will mature. Now if we just say like it's just for good chemistry and AWS to create something very innovative out of the world, I think we are humble, at least on the AWS side, and even good chemistry. I believe like we believe in the power of multiple, the force multiplier, as we say at AWS, combining the effort, use that crowd intelligence, use the researcher, use the high schooler, and the people like in between, like me, who are half in now classical side and now getting up in quantum, and Nicole and Valentin, to come together and help, right? And that probably mean like working as a software developer, or even like having your own experiment, your own passion created, right? If you see up on the screen, if you want to work for a cleaner, healthier world, good chemistry and AWS might be one option where you can start using these packages and even give the feedback what is going well with this experimentation when you are downloading the package, or what improvement you need. So with that, I think there is a survey link which our host have put. So please fill those survey and keep us. That will generally keep us honest, like how we should be bringing more topic to you guys, and then it further helps to refine our approach. But great show, Valentin, Nicole. Thanks for organizing Kruti.
Thank you.
This is the beginning, and I look forward to work with you all.
Thank you so much, Parminder. And yeah, as Parminder said, please fill out the survey. It'll really help us improve. Let us know what we did well. Let us know how we can improve. We'll definitely try to look at it and try to do our best the next time. And thank you so much, Good Chemistry team, for joining us today and giving us insights into your QEMIST Cloud and Tangelo. We definitely learned a lot more than we knew when we started off with the Howdy Partner Show. And thank you to everyone else. Thanks, Art. Thanks, Parminder. And thank you to James and James from both the companies, as well as Anish, who are on the back end helping us out. And yeah, we also have another show next week with Heimdall Data. So please tune in at 2 p.m. PT on Wednesday next week. Again, yeah, please fill out the survey. Art, do you have any last minute things that you want to discuss?
Thanks, Kruti. No, I think you got it all. This is a really, really great show, and just really thank you so much to Nicole and Valentin and the team for joining us today. I definitely learned a lot, and I'm looking forward to continuing the work and seeing what the future looks like. I think there's a lot of great work to be done, and y'all are already, doing that. I did put the LinkedIn for Valentin, Nicole, and then James from the Good Chemistry side, the LinkedIn page for Good Chemistry, your YouTube page, your website, the repos are all in the chat. So team or everyone in the audience, if there's something that you missed, just scroll up. All of the links are there. But we look forward to the next show and what the future holds. Cool.
Awesome. Thank you, everyone. And see you next week.